So we just spent some quality time with Glassboard. There's a nice job that you did, Blythe, on that. And what we discovered, we realized two things. One is that Chris was trying to trick us by coming up with this jargon called the half cycle time, when all he really meant by that was half of the period. Because the period's the full oscillation, whereas the half cycle time is just sort of, half of that oscillation. So the period of, we also realized that the period of motion for a spring system is 2 pi times the square root of m over k. And so half that would be pi times the square root of m over k. So, so Blythe, can you put that in the calculator and see what we get? And hopefully that will agree with the answer in our program, which was 14.
So I have m over k. Our m is right now just 10.
Mm-hmm.
K is 0.5.
Yep.
I'll take a square root. I guess, okay. I didn't know I did it that way. Delete this. I'll just do it from left to right. So we have pi 3.1459
Mm-hmm.
times the square root of m over k. So our m is 10 and our k is 0.5. And that's 14.05.
There you go.
It's very close to what we had printed on our screen.
Yeah, very, very close. So we did it. So our code is working. It could have been anything, but it worked out. Now the cool part is that it. Do you see that equation anywhere in the code? Do you see pi times the square root of m over k anywhere?
Nope, there are no square roots for sure.
No magic tricks here. Okay, it just, again, because we're simulating the system, we're calculating the accelerations and the velocities. That just falls out of it. It's not that we've conspired to make sure that that's true. So that's part of the fun. Now, when you did that calculation, Blythe, is there something that we forgot to put into there?
Yeah. So the spring is pressing against the blob,
Mm-hmm.
but the blob is also attached to, or the ship is also attached to the blob. So the spring has to push both those masses as it moves.
Yeah. So there's the additional inertia of the ship, and so that's gonna it's gonna slow things down,
Mm-hmm.
right? So why don't we go ahead and put that into the code?
Yeah.
And let's just do the simple thing, which is just to change this so that it has the mass of the blob and the mass of the ship. See what we get.
Okay, so I'm gonna relaunch this. Now if I move that, we get slightly larger half cycle
Mhm.
time.
About 16.
Mhm.
Do you want to run the numbers on the calculator to see if that
Yeah.
matches up with what we'd expect?
So instead of 10, we should have 13 because there's the 3 from the ship. Everything else stays the same, and we get 16.02.
Great. So it works. Now here's the thing. So go ahead and run the code, but instead of having the ship fly into the blob, just give the blob an initial velocity and see if that matches up. Because what half cycle time should that have if the ship is not collided?
Well, it should go back to 14.
Should go back to 14, right? So let's see if that happens.
Stop. So our VX blob right now is 0. We'll have it push that way. Now if I run it, I don't send in the ship. Ooh, I still get 16.
Ah.
So that's too quick in updating.
Too slow.
Yes.
It's too slow. It takes longer. Right.
Oh, I mean, I edited the code too quickly.
Oh,
I
yeah.
think.
Okay. All right. So how do we make this program smart enough to make sure that things are behaving as they should?
If I go down here, we only want this mass from the ship if the ship and the blob have actually collided.
Right.
And we have this statement right here that already is conditioned on that collision.
Right. So why don't we just move this whole code inside of the if statement and just remove it from where it is. And you might want to set the initial speed of the blob to 0 before we do that. Oops. Okay, so go ahead and fly into it and see what happens. Okay, so we get 16. By the way, the first time that you hit it, it might give something different than 16. You just got to let it, give it a little bit of time to go back and forth. But how does that look? Does it look pretty good?
It looks good.
Looks
Although I
good.
didn't measure it without the...
That's a good point. So let's,
Ouch.
okay. So let's try to do what we did before and give the blob initial speed. Don't collide with it. And then we'll see if that actually oscillates back and forth.
Okay.
And there's no, it doesn't do that at all. Okay, so what are we gonna do here? What do you think we should do to try to fix this?
Well, now there's only a spring force if the ship and the blob have collided. And we still want there to be a spring force, even if
Yes.
the collision hasn't happened.
Yeah. So we probably want to take the spring force, put it back up here, because we always want to calculate the spring force, whether or not it collides, right? So that'll be part of the solution. Do you think that's enough to get it to work?
So I think we need a version of this delta VX blob, even if there is no collision, but where we just have the mass of the blob.
Right. So basically the same thing we had before, like at the very beginning.
Right. So I put this here, then I can accelerate the blob, but if there is a collision, it can replace that value.
Right. Yeah, the computer's going through this line by line, and so if we set this variable here to this, later on it can set it to something else, if there's a collision. So let's see if this works. My fingers are crossed. I'm optimistic about this one.
Alright, let's see if I had that initial speed. Alright, so
go.
now we're at 14 and I can launch it. And go back to
Yay!
16.
Perfect. Great. All right. And so this is the kind of thing you have to do with codes. You have to come up with all the different scenarios in which you're going to use it, so that it doesn't just work if the ship collides with a blob. It also works with if the blob isn't colliding with the ship, and it also works if the blob is oscillating, and then the ship collides with it. Things like that. So you got to make sure your code is flexible enough to get all those things right. And again, nowhere have we used pi times squared of m over k to make sure that this comes out the right way. So I think the next thing is to add damping to it. Is that what it says?
There are these exercises with the. I guess we kind of already talked about the half cycle with it attached.
Mm-hmm. Yeah. So one of the fun parts about talking about springs, and one of the fun parts about using a code to do this, is that it's a little tricky to incorporate damping into like when you're in a typical course. Trying to deal with damping just with like pen and paper and maybe a TI calculator is a little can be
quickly.
Yeah, but because we are calculating everything on the fly, it's actually remarkably easy to put in like a drag force, which eventually is going to bring this thing to a stop. And my advice for putting it in is that if we just add this as sort of as if it's like part of the spring force. I mean, it isn't part of the spring force, but in terms of the code, that's probably the easiest place to put it. So in other words, what we should really do is we should really say, all right, well, there's a net force here, there's a spring force and a drag force, but let's just, it's among friends here, so let's just modify that spring force to add this damping term. And that term, so go ahead and do your thing, Blythe. That term is going to be proportional to the velocity, so it's going to be a constant times the velocity. And then there's going to be a minus sign there, which is really important because if your velocity is positive, the drag is going to be opposite to that. So that minus sign is very important.
So just adding that B constant.
Right.
To go
right.
To
Thanks for remembering that.
F spring.
Yep.
I'll have Vx blob times B.
Time I think, but let's go ahead and see what this does. So
Maybe I should start from rest.
yeah, and go ahead and give the ship an initial speed so it slams into it. Yeah, from rest.
Okay, so we're setting the blob back to 0. And I'll just go ahead and give this an initial speed left. So it slams in.
So far, so good.
And now for the first time we see these amplitude peaks decrease. They're not all lined up. So the oscillation is getting smaller. You can barely see it.
Yeah, you have to really stare at it to see if it's still moving. But yeah, so it works. So we added damping, and indeed it does slow this thing down.
Oh, I was supposed to use 0.1.
What did you use?
0.5.
0.5. Okay, well that's fine. So you put 0.5, so that slows it down seemingly to a stop rather quickly. If you want to do 0.1, we can watch it maybe oscillate it a bit more. By the way, do you know what type of oscillations this is in terms of the 3 different types of oscillations? There's the underdamped, overdamped, and critically damped. So is this underdamped, overdamped, or critically damped? Pop quiz for you.
think it's just underdamped.
Yeah, so that's right. So if you just have a small amount of damping, that and you have many oscillations before it comes to a stop, then that's considered underdamped. But if you put, I mean, fun thing you could do is you could put a damping coefficient of like 10 or something, and that would be overdamped. So I don't know, maybe you want to just try that.
Yeah, it's decaying much more slowly now.
Right.
Okay.
So what are you going to change it to?
Yeah, let's try 10.
10? Okay. See what it does. Wow. So that's the thing about overdamped is that there's so much damping it basically doesn't even oscillate.
Right. Just
Yeah.
goes straight
Right.
down.
Okay. Cool.